Okay, good morning or good afternoon. This is the solutions to our sample problems that was posted in our Moodle. So I will be solving them, and please take note these are already pre-solved so that the video would go faster. You should answer this on your own, especially those with longer computational parts. So let's start with the first one. What is the freezing point of a solution prepared by adding 140 grams of trichothecene to 0.746 kilograms of benzene? The freezing point of pure benzene is 5.5 degrees Celsius, and the freezing point constant for benzene is 5.12 centigrade per molal. Okay, so what we need to do first is to get the molecular weight of our trichothecene, which is C19H24O5. Since we know the molecular weights of these compounds or this these atoms, carbon is 12, hydrogen is 1, oxygen is 16. So 9 times 19 times 12 is 228. Our hydrogen is 24 and our oxygen is 5 times 16. We have our 80. Our molecular weight should be the sum of these values, 332 gram per mole. So let's write it here. So that we have the value for our trichothecene. Oh, I'm gonna erase the screen first. 3, 3, 2. Okay, so our formula for freezing point depression is change in freezing point or change in temperature. Change in freezing point equals Kf m, in which Kf is our freezing point constant. Okay, so what we need is actually the new freezing point. Okay, so we will get this value first so we can get the new freezing point. Okay, so let's start solving. Kfm delta T equals 5.12 centigrade per molal times 140 grams were added, so 140 grams over the molecular weight, which is 332 gram per mole, over the weight of benzene in kilograms, so 0.746 kilograms. Simplifying it or solving the problem, so the upper part of the fraction would yield 0.4216 moles, while the weight still is 0.746. 5.12 times 0.565 molal. So this will cancel out, and our change in temperature is 2.894. Now this is not the final answer. This is only the change in freezing point or our freezing point depression. What we need is the new freezing point. So our new freezing point equals our pure freezing point or freezing point at pure minus our new. So to get new, I mean this should be freezing point depression. Sorry. Freezing point depression equals pure minus new. New equals pure minus F depth. So new is, what is our pure? Our pure is 5.5. less our freezing point depression of 2.894. Our new freezing point is now 2.605 degrees Celsius. It is still positive because we started at positive 5.5 degrees Celsius as our freezing point. Okay, so for our next problem, it is again a problem in freezing point depression. How many grams of pyrazole will have to be dissolved in 736 grams of camphor to lower the freezing point by 15 degrees Celsius? The freezing point constant for camphor is 40 degrees per molal. Okay, so again, what is our formula for freezing point depression? Change in temperature is our KFM. So our KF is, our freezing point depression is this one. Okay, and we have our KF here. We also have the grams of our solvent, and we are now looking for how many grams of pyrazole would have to be dissolved in 736 grams of camphor to lower the freezing point. So since we already have the data, let's plug it into our formula. So 15 degrees Celsius equals KF, which is 40 Celsius per molal times. Let's convert this into kilograms first. So this is 0.736 kilograms. 0.736 kilograms. And then what we have above, instead of doing it the whole way, what I prefer to do is to get the moles first. So this is actually a two-step problem. Okay, I'm going to move all the variables to one side and move the missing variable on the left side. So moles pyrazole over 0.736 kilograms equals 40 degrees Celsius over molal. Let's have mole per kg instead para mas maliwanag. Times. No, sorry. It should have been 15 degrees Celsius first. Then we have mole per kg here on top over our 40 degrees Celsius. Okay. Simplifying it further, we have 0.375 mole per kilogram mole over kilogram, since we already removed Celsius. Then we have moles pyrazole over 0.736. Let us divide both sides by multiply both sides by 0.736. This is in kilograms. So this would be removed. This would be removed. Now our moles pyrazole should be 0.276 moles. So this is not the final answer. Why? Because what we need is grams. So to get grams, we need to multiply the moles. Yes, we need to multiply the number of moles by our molecular weight. So let us save some part of the screen here. So 0.276 moles. We still don't have the molecular weight. So C3H4N2. C3 is 3 times 12. H is 1. N is, nitrogen is 14. 36, 4, 28. And the sum is our 68. Okay, multiply it. So 1 mole of pyrazole is equal to 68 grams of pyrazole. So the amount is 18.768 grams. You need 18.768 grams of pyrazole to decrease the freezing point by 15 degrees Celsius. Okay, so we have problem number 3. This is again related to our freezing point depression. When 20 grams of an unknown non-electrolyte compound is dissolved in 500 grams of benzene, the freezing point of the resulting solution is positive 3.77 degrees Celsius. The freezing point of pure benzene is 5.444 degrees Celsius, and the freezing point constant for benzene is 5.12 centigrade per molal. What is the molar mass of the unknown compound? So what is being needed? What is being needed is our molar mass. We can get this to our conventional formula. It is similar to our previous question. However, this time we do not know the molecular weight. However, we do know how much of the compound was added. Okay, so first let us start with the data we are given. We are given Kf. We are also given freezing point of the pure solution, and we are also given our new freezing point. This is the new freezing point. So with this, we have our pure minus new Fp. We can get our freezing point depression. So 5.444 minus 3.77 degrees Celsius equals our 1.674. This is our delta T, or our freezing point depression. Let us plug it into our formula. Freezing point depression equals KFM. 1.674 degrees Celsius equals Kf, which is 5.12 degrees Celsius per molal, multiplied by our molality. So our molality is actually lacking. However, we can substitute mole for a while. So moles, let us assume moles. We are solving for moles, so it is easier. You can an alternative would be 20 grams times x over 1 mole. This is the alternative. Okay. However, I would prefer it to do it this way, so in which it is a two-step problem. Moles per kilograms of solvent, we have 500 grams, so that is 0.5 kilograms of benzene. Again, I would like to isolate moles on one the missing variable on one side, and all the other variables on the other side. So moles over 0.5 kg equals 1.674 degrees Celsius. Class, please take note of when I am moving the variables. What you might do is move it unintentionally. Okay, multiplied by 5.12 degrees Celsius mole per kg. Okay, and the resulting value should be moles over 0.5 kg equals 0.3269 moles over kg. So where did this come from? Centigrade was cancelled out. Let us divide both sides by multiply both sides by 0.5 kg. So we will cancel out kilograms, and our moles is 0.1634. We have 0.1634 moles. However, this is not the final answer. Again, we are looking for the molar mass. Remember that to get the number of moles of a substance, you need to multiply the grams, or the mass of the substance, by the molar weight. So moles equals our grams times molecular weight divided by molecular weight, I think. Yep, divided by molecular weight. I got confused. Okay, moles equals, we have 20 grams over, we don't know the molecular weight, but we do know the moles, so 0.1634 equals 20 grams over, oh, sorry, it was wrong. Yeah, over x. Okay, so let's substitute. X equals 20 grams over 0.1634. This is mole. So gram per mole is actually molecular weight. X will become 122.4 grams. So this is your molecular weight of that substance. Okay, for our next problem, this will cover our osmotic pressure. So, calculate the osmotic pressure exhibited by 0.42 moles of benzene solution at 30 degrees Celsius. So, what is our formula for our osmotic pressure? It could be PV and RT, or it could be P equals CRT. I would be electing to use this one since we already have concentration in molarity. Please take note, class, that it only applies for molarity. If you have normality, you still have to back convert it to our molarity before we continue. Okay, so pressure equals concentration, our gas constant, and our temperature. We are computing for osmotic pressure, so this formula is fine. P equals 0.42 moles per liter multiplied by our gas constant, 0.082 liter atmosphere over Kelvin mole. Multiplied by our temperature, it should be in Kelvin. So let's simply add 273 here, and we will have 303 Kelvin. So this is very straightforward. Simply reduce the units. Liters is liters, moles, Kelvin, and Kelvin. And you simply need to multiply and divide afterward. So the pressure is 10.435 atmospheres. Very straightforward. Okay, moving on to our next question. What is the current temperature of a solvent system in centigrade if the osmotic pressure is 6.27 atmosphere with a molarity of 3.2 and a volume of 4 liters? Okay, so again, what is our formula? We have PV and RT, and we also have P equals CRT. I would like to elect to use this one since we have a specific volume in our problem. So PV equals nRT. Our pressure is 6.27 atmospheres. Our volume is 4 liters. Our amount of substance, or our moles, is we can get it by 3.2 moles per liter times the volume, which is 4 liters. So this is simply to get N. Then we have our gas constant, 0.082 liter atmosphere mole Kelvin. And we are actually lacking temperature. So let us isolate everything to one side and leave Kelvin on the other. Okay, so Kelvin equals 6.27 atmospheres multiplied by 4 liters over 7.2 moles multiplied by our gas constant in the inverse mole Kelvin, then 0.082 liter atmosphere. So class, please remember that the units should be in the proper order. So hindi kayo nalilito or you won't get the wrong answer if you have a unit that is squared. So atmosphere, moles, liters. What we have is Kelvin, and the answer is 42.47 Kelvin. However, this is not the final answer since we are looking for centigrade. So we simply need to subtract 273 Kelvin to get centigrade, and the answer is negative 230.52 degrees Celsius. So this is almost negative 0.